Okay, welcome back everybody. This is Sandipan's second lecture, and he's going to continue telling us about a quantum field in a box. So just before I forget, the next lecture on 18th August, so that is the final lecture, we are going to start it half an hour earlier. So it will be at 10 a.m. Indian Standard Time. Okay, Sandipan, it's up to you.
So today I'm going to discuss a very specific CFT theorem. This CFT theorem is going to be particularly useful for CFTs that are dual to effective field theories in ADS. But actually, the techniques that were used to derive this theorem can have general applications. So let me spend some time on this theorem. Particularly, let me describe the derivation of the theorem step by step so that all the assumptions become really clear. And also, if somebody wants to use this kind of techniques for other applications, they can do that as well. So last time, what we saw is the following. In the last lecture, basically, we saw that the space of effective field theories, there is a space of effective field theory, but only a subset of these effective field theories, they come from something which is every complete. So this is basically the space of consistent EFTs. And also, we saw that if we take this idea and if we put it in ADS, we get a dual CFT. Now, because of this low energy effective field description, we have some partial information about the dual CFT. For example, we know some of the low-lying operators. We know there is a scalar operator. We know there is a stress tensor. We know other double trace operators. And also we know the OP coefficients. And in particular, we know some of the safety correlators. But we don't know the entire CFT. We only have information about only certain aspects of the CFT. But even though we can compute safety correlators, mainly some safety 4-point functions, so this safety 4-point functions, they must satisfy many consistency conditions. That's because this information must be consistent with safety axioms. So we can derive many consistency conditions that these safety correlators must satisfy. Some of these consistency conditions can be trivially satisfied. Some of these conditions can be important, but they might not be interesting for CFTs that are dual to effective field theories. For example, they may not tell us anything interesting about the dual effective field theory. So the goal of this talk is to derive interesting consistency condition on safety correlators. So the goal is to find constraints that are interesting for the dual effective field theory. Before I can do that, I need to actually answer one very important question. So what is the right safety correlator to study? basically we have to first find out the right safety correlator, and then we can go ahead and study that correlator. So the question is, actually, we know the answer to this question, and there is an obvious answer, which is basically the CFT Regi correlator. So the reason these are interesting correlators for our purpose is because we already know CFT Regi correlators, they obey certain certain interesting constraints, such as the chaos bound. But there can be other constraints as well. So we know that probably if we study CFT Regi correlator, we may derive some interesting constraints which are similar to the chaos bound by Maldacena, Shankar, and Stanford. The second reason is, so let's say we derive some constraint by studying this CFT Regi correlator. So the CFT Regi correlator, for theories that are dual to ADS effective field theories, so the CFT Regi correlators, they describe high energy scattering deep in the bulk. So basically, they describe kind of local physics in ADS. So if we find some constraint by studying Regi correlators, it is very likely that these constraints are insensitive to space-time curvature. So this is a very important property. And the third point is, so it is also known that Regi correlators obey some very nice analyticity and positivity conditions. So that provide us with a certain amount of mathematical control. So this is something nice to study.
Sandipan, sorry, just to understand. So the aim was to understand, the coefficient in a QFT, how they are bounded, etc. Right? So you calculate a S matrix there. So I thought you would look into CFT something which is natural for S matrix, not any other thing, right? Is that also the motivation of the the Regi correlator is going to go there directly?
That's right. So any Regi correlator, basically they have information about like high energy scattering in flat space in some sense, because they are basically high energy scattering in ADS, and because they are like local processes, they are expected to be insensitive to ADS curvature. So, but they are not exactly equivalent to ADS scattering, but they are very close to some scattering amplitude in ADS.
I see. Okay. And you will relate this directly to the calculation in the field theory side, right? At the end?
Not really. So there are two different approaches one can take. So I can try to relate a CFT correlator directly to some flat space scattering amplitude, or I can just study some CFT correlator which is analogous to scattering amplitude, and just derive constraint on the EFT coefficients from that CFT correlator without relating it to some scattering amplitude.
I see, but how will you connect to the EFT picture? You had a EFT, then you put it in the ADS, and then you are calculating some CFT. How are you going to connect precisely?
So today, what I'm going to do, I'm going to just derive some CFT constraints which do not know anything about the bulk EFT or things like that. It's just some CFT constraints. Then what you can do, you can actually compute those correlators by starting from the dual EFT.
Okay, I see. Okay.
So basically, that's the picture. So since I can compute these CFT correlators because of the dual EFT description, so then I can just use the CFT theorems.
Okay. Okay. Thank you.
Okay. Let me now describe the CFT Regi correlator. First of all, just some convention. So the space-time points are denoted by time, a special direction, any special direction, which I call y, and vector x is the rest of directions. So that's how I'm going to denote my points. Sometimes I'll also use light cone coordinates. So x minus, x plus, and x, where x minus is t minus y. So this is the time coordinate. So this is t, this is y. So this is x minus, x plus. So I have one operator O. So let me use some. So this is at y equals to -1. This is at y equals to 1. And just for simplicity, let me call this O at x1. And this is O at x3. Similarly, I have two more operators. One somewhere here. Somewhere here. So let me call this O at x2, O at x4. Let me also write down the x minus and x plus coordinate of this operator. So this is the configuration. Let's see. Okay. So I have a 4-point function. which is function of rho and rho bar, because the two O operators, they are at -1 and +1. So we have this particular 4-point function. Let me note one more thing. So this is the light cone of the two operators on the y-axis. So just to note, so these two operators, they are time-like separated. These two operators, this pair is also time-like separated. So some of the operators in this correlator, they're time-like separated. So the ordering of operators in this correlator, that does matter. And the operators are ordered as written. So this is a very specific Lorentzian correlator. Now the Regi limit is best described if I just perform a coordinate change or field, just a redefinition of rho and rho bar. So the Regi limit is when I take sigma to 0 with eta fixed and between 0 and 1. So this is the Regi limit. Pictorially, what it does, it's basically I'm taking this operator and this operator to infinity, and so basically these two operators, they are approaching the light cone and they are approaching infinity at the same rate. So that's what this particular limit says. Any question or confusion or anything at this point?
Sandipan?
Yes.
Is there an order in which you first take it to the x plus axis and then along the x minus axis?
Actually, they are. So if you look at this scaling, it's basically it looks exactly like this arrow. So it's basically approaching the light cone and at infinity at the same rate. So if to be more clear, let me actually show it. So this distance is basically this is eta times sigma, and this distance is 1 over sigma, and the limit is sigma goes to 0.
Thanks.
Okay. The next thing is the assumptions, or CFT axioms in this case. So in the last lecture, when I was reviewing the bounds from the amplitude consideration, I had to assume many things about the UV amplitude, some things like unitarity, crossing symmetry, analyticity. In this case, actually, I don't actually have to assume much. Only thing that I need is basically there are OPs in CFT, and the second condition is unitarity, which in this case, the statement that all the OP coefficients, they are just real. And obviously, we have conformal invariance, but yeah, that's a given. So these are the only things that I'm going to assume, and these are well-established axioms, so I don't think anybody will disagree. Now, using these axioms, let me derive an analyticity property of the Regi correlator. This is a well-known thing, but let me still go over it. So first, let me consider the Euclidean correlator, which is basically this correlator, but in the regime so pictorially, let me see. So let me. So this is when the operator O so the operator OX3 is inside outside the light cone. So that's why it's an Euclidean correlator, because all the operators, they are space-like separated. Okay. So this Euclidean correlator I can expand it using the OPE. I can expand this as follows. Remember that this is a normalized correlator where it's divided by the 2-point functions, as shown here. So Z bar in this case so the first thing I can ask, as a function of complex rho and rho bar, first when is this correlator? When is this Euclidean correlator analytic? So this is a very easy question to answer from the conformal block expansion. So both for rho and rho bar, as a function of complex rho and rho bar, this correlator has branch cuts from 1 to infinity and from 0 to minus infinity. And this is the Euclidean regime between these two branch points. But we actually care about the situation where some of the operators are time-lag separated. So we can compute the Lorentzian correlators where some of the operators are time-lag separated directly from the Euclidean correlator. So the easiest way to do that is basically the standard I epsilon restriction. So I'm not going to show you exactly how to do that because it's the standard I epsilon restriction. There is nothing new about that. But I'm going to give you some examples. So the first thing to consider is let me go back. Okay, so we had this correlator over here. I can define another correlator, G not rho rho bar, which is same set of operators, but the ordering is different. So the operators are given here. So again, these two point x1 and x2, they are time-lag separated, and now point x3 and x4, they are time-lag separated. So the difference between this correlator and this correlator is basically the ordering of operators. So G naught is actually very easy to calculate from the Euclidean correlator. So we have this Euclidean correlator, G naught when rho is greater than 1 is basically G Euclidean correlator that was here, which if you look at the right hand side, it's a function of only Z and Z bar. So just use rho greater than 1 in this expression, and you get the correlator. So basically, this G naught correlator is obtained directly from the Euclidean correlator. In some sense, like you can still call it an Euclidean correlator because it's exactly the Euclidean correlator. You're just changing Z and Z bar. That's it. And because of that, this is also real, and it has many other nice properties that I'll discuss later. But obviously, G0 is not the Regi correlator. So the Regi correlator, let me stay in this page. So now I need to find out the Regi correlator. Let's see. So which was generated just by the symbol G. So this particular operator ordering, if you perform the standard I epsilon prescription, you'll see that the way to get it is the following. So first of all, since rho bar is always less than 1, so rho bar is somewhere here, let's say. But for rho, we start with a point which is below 1, and then we analytically continue above the branch cut. So this gives you the Regi correlator. In other words, start from the Euclidean correlator, take rho to this and rho bar with epsilon greater than 0. That's how you can compute the Regi correlator. So this is an important expression for. So this implies the following condition. Let me call that condition 1. So the Regi correlator is analytic for greater than 1. Let me much greater than 1, as long as rho bar is between 0 and 1, and imaginary part of rho is positive. So this is condition 1. The reason is, if you keep the imaginary part of rho positive, that means basically you are in the so you are in this regime. And in this regime, as you can see, there is no branch cut or there is no singularity, so the correlator is analytic. But so basically, the important point is you are not crossing the branch cut. You are always above the branch cut. Any question?
Sandipan, I'm sorry. Can you, from the picture once, can you explain the 3 correlator that you just said? So first is Euclidean is what you have done. And then G is I do nothing. I just get, and for this Regi thing, I just take rho bar is whatever rho I take it to be that way. Is it the?
Yeah, so okay, I can actually explain it again in this picture. So okay, I think this is a better picture now. So Euclidean is basically when, like, we are never moving this this operator and this operator. They are fixed. So the Euclidean correlator is when the x3 and x4, they are basically they are space-like separated from x1 and x3. So basically, that's the Euclidean correlator. So in terms of rho and rho bar, this situation is rho is between 0 and 1. Rho bar is also between 0 and 1. So that gives me Euclidean correlator. Then the second one is basically the one that I call G0 rho bar. This is when I move it here. So now things are time-like separated, but the ordering is this. This is the ordering. Now, if you use the I epsilon prescription, you'll see that. So to go from the Euclidean correlator to G0, you don't actually have to cross any branch cut. It's basically the same Euclidean correlator. Only thing that it's basically just use the value of rho and rho bar to compute Z and Z bar. That's it, and plug that in. So in this case, rho is above 1, but rho bar is this. So in some sense, this is the time ordered correlator. And the third is the Regi correlator, where the operators are exactly at same position, but the ordering is different. This is the ordering, and if you check, it's not time ordered. It's out of time ordered correlator. And in this case, again, rho is greater than 1, and rho bar is between 0 and 1. And the way you should have to take rho to greater than 1 is basically you have to keep the imaginary part of rho has to be positive. So basically, so that you don't cross the branch cut.
I see. Okay. And so just a very nice thing. And what happens? How do I identify with the Euclidean correlator? Z of rho, that the identification that you gave, it remains the same, is it?
So that identification remains the same. So it's, yeah, so these two expressions, they remains the same. Okay. But if you plug that in, you have basically, first you have to calculate the conformal blocks. So that's where this analytic continuation will come up.
I see. Okay. Okay.
So in terms of Z and Z bar, what happens is basically, if you like convert everything in terms of rho and rho bar, then you will just see when you write down this conformal block expansion, you'll see that there is a branch cut, and basically then you have to go above the branch cut. And if you write everything in terms of Z and Z bar, so for the Regi correlator, what you have to do, you have to rotate Z around 1 and then again come back below 1.
Okay, thank you. Thank you.
Okay, so this is the condition 1. Now I'll talk about a positivity condition.
Sandipan, can I ask you a very naive question here? So there is a singularity, that the apparent singularity at zeta equal or whatever rho, whatever the variable you're calling. Is that rho or is that zeta? G of rho and rho bar, or zeta and zeta bar?
Rho and rho bar.
Okay, rho at -1. There is an apparent singularity. So what is the meaning of that?
Rho equals to -1, or rho, can you say that again? Rho equals to -1, you said, right?
Yeah.
So rho equals to -1 is basically, let's see. So that's because, so this operator, when you take rho to -1, this is basically, you take it from here to the other side, and then basically it's hitting the light cone of this operator.
It's going to hit the light. I see. I see. Okay. Thank you.
Okay, now let me talk about a positivity condition. We again start with the Euclidean correlator. But we expand it in the first we expand it in the direct channel. So that is, as we saw before, we have this conformal block expansion. So there is something very interesting that one can derive just from CFT axioms. So from CFT axiom, we know that this is positive because the OP coefficients are always real. And also one can check that you can actually expand these conformal blocks in row and row bar. And any conformal block, when you expand in row and row bar with this identification for Z and Z bar, that also has a positive expansion. So this is a fact that anybody can check, and this follows simply from the conformal block expansion. So from there, one can check and one can actually show something really nice. One can show that this Euclidean correlator has a positive expansion. All of them are positive. So there is an alternative way to derive it. So if you assume reflection positivity, even from there, you can also derive that this P coefficients, all of them should be positive. So but in safety, you don't you can do better. You don't actually have to assume reflection positivity. You can just derive reflection positivity from the safety axioms. Okay, now see one thing. So these two expressions, they are equal, right? Because they represent the same quantity. One is a function of Z, and the other one is a function of Z and Z bar. The other one is a function of row and row bar. So what you can do? So basically, you can write down a general expression for this sum. So by equating these two, we can write down we can solve in the previous expression, in the second expression here, we can solve for row and row bar from this definition of Z and Z bar. So we can solve for row and row bar in terms of Z and Z bar. We can just plug that in here. So we get something really nice. So this is true. This is valid for any Z and Z bar between 0 and 1. So this is an important expression for today. Okay, now we can do something useful from this result. Now we can take the same Euclidean correlator, but we can expand in the cross channel. So if we do that, we get now z and z bar is different. It's 1 minus rho square. Now look that we have the same quantity here. So this is the quantity that we have here. So we can just use this sum in terms of B H bar. So if I do that, I find the following result. So basically, I use this Z and Z bar and plug it in here. So this gives me this expression. The reason why this is very useful, because now from this expression, I can compute the other two Lorentzian correlators, G0 and the Regi correlator, both. So the first one, first let me write down G0. So this is basically, as I said before, you don't actually have to do anything. Just take this Euclidean correlator and just plug in rho and rho bar. If you do that, this is what you get. So now rho is, this is for rho greater than 1, but rho bar is between 0 and 1. So if you look at this expression, as I said before, this is positive, and all the other terms, they are also positive. So this is basically, if you check, this is always positive. And this should not be surprising. This follows from, this also follows, this is basically the Rindler positivity. If I assume Rindler positivity to begin with, then I don't even have to derive this positivity condition. It follows from that. But as I said before, in CFT, you don't actually have to assume anything beyond the existence of OPE and unitarity. That's it. Now I can also calculate the Regi correlator that we really want to calculate. I have to perform the particular analytic continuation that I showed before. Once I do that, so the difference is now there is a phase factor. So the expansion is almost the same as this expansion, the previous expansion, this one. The only difference is this term. So that means basically G0 is a positive expansion, whereas the Regi correlator, it's basically each term is shifted by a phase factor. So that immediately implies, if I just take these two expansion and take the real part, so real part of the Regi correlator, this is smaller than the real part of the Euclidean correlator, the G0 correlator for so this is the second important condition. So far, let me emphasize again. So everything I said, it does not depend on the fact that whether the CFT has a ADS dual or not. This is true so far. Whatever I said, everything is valid for any CFT. These conditions, they follow directly from CFT axioms.
Sandipan, so your G0 was G0 in general rho bar. You made it to be a complex, right? By I epsilon.
In this case, it's basically okay. That's a good point. Oh, let me yeah. So that's a good point. It's basically in this expression. So rho bar, let's see. You said rho or rho bar? Rho bar is always real. So in this expression, rho is basically some real value of rho plus I epsilon in the limit epsilon goes to 0 from the positive side. So for this correlator, actually, when you take this limit, this is a smooth limit, and this correlator becomes real.
I see. Okay. What I was asking is that it's not only inequality, right? I can have also imaginary part of G rho bar to be, or the mod of, I can take, all those things are there or not?
Yeah. So you can actually derive a lot, like from this to expansion, you can derive actually many different conditions. So this is the one that I'm going to use. So that's why I wrote it down. Yeah, there are other conditions. That's right. That the condition about the mod of G, this is also true. Yes.
Or okay, I see. And this is the strongest condition, or all of them are equally?
So this one is the stronger one. But yeah, I actually don't need that condition, but because of that, I ignore it. In fact, there are other conditions that's even stronger. So for example, you can probably derive some lower bound of the Regi correlator as well.
I see. Okay.
So yeah, you can derive many other conditions from these two expansions.
Okay, thank you.
Now let me go back to the CFTs that I care about. So those are CFTs with a dual description as some EFT in ADS. So now if I look at the positivity condition that I just derived, so this condition is actually not good enough for the following reason. So this quantity on the left hand side for the purpose of our discussion, we want something on the left hand side that depends only on the interacting part of the EFT. So that's when I can use it. So if I don't have the disconnected part eliminated somehow, I'll not be able to use this condition to derive some constraint on the coupling constant of the interacting part. So just to show you that this is not good enough and why it's not good enough, let's just take an ADS theory which is completely free. It's just a free scalar theory. So in that case, this G naught, it has this, we know it exactly because it's exactly a free theory. But if I look at the Regi correlator for the free case, I have the one term I also have the second term, but with a correction. The second term is basically the same with a correction of a phase plus the third term, which is exactly the same. So now if you look at the difference, so now if you compute this quantity over here, so even for the free case, it's not zero when delta is non-integer. So in general, when delta is non-integer, so this quantity here, it's still non-zero because of this phase factor. So we want a positivity condition which will vanish for the free theory. And actually, it's very easy to actually derive it just from the previous expansions, from these two expansions. What I can do, I can just isolate the identity operator from both of this expansion, and I can actually derive the following thing. I can define a subtracted Regi correlator, which is the Regi correlator of the interacting theory minus that of the free theory. Similarly, for the G0, I can also define a subtracted and I can do the same trick. I can play the same game, and I can derive the following condition. Now, the good thing is the contribution from the free part of the action that basically drops out. So that saturates this inequality. So that means basically the difference of the left-hand side minus the right-hand side, that has information only about the interacting part of the effective field theory. So this is the second condition that I'm going to use. Before I proceed, any question? Okay. So now the theorem.
Sorry, Sandeep, I did not get, like, even if I do this, still the free part, if I just bring everything together to the left, free part will still cancel out, right? The free part will not cancel out. Is that the point?
In which expression? This one?
The condition 2 instead, where you have delta G. There, if I bring everything together to the left, let's say, the free part, does it not cancel out?
No, see, like this one has G free and this is G not free.
Oh, right. This is G not free. Sorry. Okay.
Basically, it exactly cancels the thing that we want to cancel.
Yeah. Okay.
So now we come back to the theorem. It's the easiest way to derive the theorem is by performing a change of variable. So rho to 1 over sigma, rho bar to eta times sigma, where eta is between 0 and 1, and sigma basically the Regi limit, as I said before, it's sigma to 0. But I make sigma complex. So the condition 2 over here, this is for real sigma. Now, in terms of the sigma coordinate or sigma variable, again, I can derive the following thing. Sorry. The Regi correlator, or okay, now it's a function of eta and sigma. So as a function of complex sigma, so from the condition 1 about the analyticity, it's very easy to check that it's analytic on the lower half complex plane around sigma 0. So this is sigma 0. So it's near the origin, but below the real axis, it's analytic. And so this is the analyticity condition. And in terms of the sigma variable on the real line, we have the condition that delta G naught eta sigma minus real part of delta G eta sigma, that's positive. Okay, so now I'm going to do everything in this eta and sigma variable. So even these two conditions, okay, even this condition here, and also obviously this analyticity condition and this positivity condition, even they are true for any CFT. So this subtraction of the identity at in each channel, everything is valid in any CFT. So far we have not assumed anything about the we have not utilized the fact that the dual CFT, the CFT is dual to some effective field theory. So the way I'm going to implement that, I'm going to use the following ansatz for the Regi correlator. So this is something I'm going to assume. So I assume that the Regi correlator is given by the correlator with subscript 0 plus an infinite tower of growing terms up to terms that decay in the Regi limit. So these are positive powers of sigma. And this lambda is basically is a shorthand for to denote the fact that these are decaying terms and they are also suppressed by some small parameter. So for example, for CFTs that are dual to effective field theories, this lambda can be some any coupling constant in the of the interaction. So basically, when I say they are suppressed, all I mean is basically this small corrections, they always come from the interacting part. And obviously, this part will not contribute to anything that I'm going to say next. Another important point is, obviously, this parameterization is not going to be valid for all sigma. So this can be valid up to some cutoff scale, which is sigma star. So this is something, some cutoff, sigma cutoff. So this is basically something I'm assuming. I'm assuming that the Regi correlator has this particular form within some range. The reason I'm assuming this is basically this is exactly what we'll get for CFTs that are dual to ADS effective field theories. But if you have some other CFT which do not have a dual description, but even for that CFT you have a similar Regi correlator, even then all the bounds that I'm going to discuss, they are still valid. Okay, the next step is in the complex sigma plane, let's draw this contour. So this is a semicircle, but yeah, it does not look like one. Okay, let me try to draw it again. Okay. So from minus R to R, where R is some arbitrary number which satisfies basically this condition. And this is the contour. Okay, then I'm going to study this particular contour integral. And obviously this is 0 because of the analyticity condition for any L, any integer L greater than 2. Oh, I actually forgot to mention one thing. In this expansion over here, actually, it's very easy to show that all the odd coefficients, they should be exactly 0. So this follows from the fact that all the safety correlators, they obey some standard consistency condition. For example, there is a condition like this, which basically says that in the OP of two identical operators, there cannot be any odd spin operator. So that's from there, we get this condition. So half of the coefficients are already 0. So our goal is to constrain the rest of the coefficients. So there is so we can actually divide this integral by the line integral and then the integral over the semicircle. Now, for the integral over the semicircle, so this part, so because of this condition, I can just use this expansion and I can just evaluate this integral. And for the integral on the real line or just below the real line, so there I don't know the exact correlator, but I have the positivity condition. So this gives me a very nice sum rule. So let me now just write down the sum rule. So for CL coefficients, where again CL coefficients are defined here. for any and again L is integer and greater than equals to 2. So as you can see, this entire thing inside the integral is positive. So the positivity of this part follows from the positivity condition that we derived, and sigma to the power L minus 2, that's always positive because L is an integer. So that, and also like before I proceed, let's mention one thing. So in the right hand side, this R, it's just some parameter we picked, but the left hand side does not depend on that parameter. So that's a very interesting fact. So that means basically the real part of del G is equals to real part of del G naught when sigma is greater than sigma star. So basically the integral does not depend on the upper limit of integration. So this basically gives you a definition of sigma star. It's basically when the real part of delta G differs significantly from the real part of delta G naught. So that's the definition of sigma star. Other than that, sigma star is basically a theory dependent cutoff scale, which basically which will not be able to fix, but will show that this is basically something like 1 over delta gap square. So sigma star basically plays the role of the inverse delta gap. Any question, comment? Okay, so now I can write down from this dispersion relation, I can write down the following 3 conditions. First of all, CL eta should be strictly positive for all L greater than or equals to 2. Strictly positive because CL can be 0 only when delta G naught and is equals to delta G. So let's see. So this is 0 for the entire integral. Means basically delta G naught equals to delta G. That means basically the CFT is a generalized free CFT, and that means the bulk scalar theory or bulk EFT is basically an exactly free theory. So the strict positivity implies that strict positivity is valid when the theory is interacting, and the saturation necessarily requires that it's a free theory. Then the next condition is monotonicity.
Sandipan, CLs are related to what? I'm sorry, I said no. CLs are related to what? Did you relate CLs to something?
Not yet. They are basically these coefficients.
Yes, I understand that. Yes.
So basically, so far I have not related them to anything, but basically these are the things that are determined by the coupling constant in the bulk EFT.
I see. And from the CFT perspective, this will be some OP or something?
From the CFD perspective, generally, because it's a Regi correlator, it's not going to be a single OP. It's going to be like some combination of like the leading Regi trajectory, things like that.
I see. And CL eta greater than 0, meaning I can do for any value of eta, this is greater than 0. So it will be
so this is for eta is always between 0 and 1.
From 0 to 1.
But for any value of eta, this is true.
So sorry, you derived it for eta less than 1, greater than 0, but now you are saying it is true for any eta. Is that the point?
No, like it was derived for eta between 0 and 1. So eta was a free parameter throughout.
Okay.
So it was derived for some specific region in rho bar plane. So that's basically this region. In terms of eta, it's basically from 0 to 1.
I see. Okay.
The monotonicity condition is basically, you can just take in the sum rule. You can check that the ratio of CL plus 2 and CL, this is always suppressed by sigma star square. And sigma star, as I said before, it's much less than 1. So this is a very small number. So this is a parametric suppression. And the third condition is the condition of log convexity. So the first two conditions, they are linear relations, but you can derive a non-linear expression. So when this has to be true for all integer L greater than or equals to 2. So all three follows from this relation. Any question? So, okay, so this is the main result from today's lecture. And this is something that I'm going to use in the next lecture to derive constraint on the scalar EFT. Let me conclude by making some important comments. First of all, as I said before, this set of constraints, they'll lead to precise bounds on EFT coupling constants, especially coupling constants of higher derivative interactions. And the second thing is about the chaos bound. So if you look at this expression, so there are terms like 1 over sigma. So the Regi correlator has terms like 1 over sigma plus some number 1 over sigma cube. Not just, and also these coefficients, let me write them down. This is C2, C4, C6. And if you look at the positivity condition, it's a strict positivity condition. That means all these terms, they are non-zero. So naively, it looks like the chaos bound is violated, because a naive interpretation of chaos bound would be that the Regi correlator cannot grow faster than 1 over sigma. But as we see here, there are there are terms that grows faster than 1 over sigma, and their coefficients are strictly positive. So obviously, one can ask, is there a contradiction? And the answer is no, because the right interpretation of chaos bound is not that there cannot be any term that grows faster than 1 over sigma. That's not the correct statement. If I compare these two terms, and let's say the next term, from this relationship, I know that C4 is less than sigma star square C2. So this term is basically this. The second term is less than C2 sigma star square sigma square, and then 1 over sigma. Now, if I compare this term and this term, and since this expansion here is valid only for sigma greater than sigma star, so this contribution is always strictly less than the contribution from the 1 over sigma term. And similarly, you can show that this is true and all the other terms.
Sorry, do you mean the other way, or this is the less than or greater than? I'm sorry.
Oh, yeah, you're right. Yes, yeah, that was a bad typo. Yes, that's right.
But sorry, I did not get something. But these are smaller, but still these are chaos bounds. They cannot be there, right? That's what I thought. That's what you said.
So that's the naive interpretation of the chaos bound. So as I showed here, that if the 1 over sigma term is there, then like the other the other growing terms, they have to be there. It is not even that they can be there or they cannot be there. They are there.
I see.
So because if you look at this dispersion relation, so the only way any CL can vanish if the integrand is exactly 0. And if the integrand is exactly 0, then not just one CL, all the CLs they will vanish.
Right. I see.
If C2 is non-zero, then C4, C6, they have to be non-zero. So it's basically the way you should think about it. It's basically exactly in effective field theory. In effective field theory, it's not that you can have one higher derivative interaction. As soon as you add one, all the other higher derivative interaction will also be there.
I see.
So the statement that there cannot be any term that grows faster than 1 over sigma, that's a wrong interpretation of the chaos bound. The right interpretation, and actually that's the standard interpretation of the chaos bound, is the following. So the way you should interpret the chaos bound, it's basically the MSS bound. Basically the following statement. There is no range of sigma, however small, over which any term that grows faster than 1 over sigma in the Regi correlator. Dominant. So basically, this is the right interpretation of the chaos bound. The statement is there can be 1 over sigma cube, 1 over sigma to the fifth, those kind of terms. They are there, but they can never dominate over the 1 over sigma term.
Sandipan, this is an infinite sum that you sort. So that will still be okay. Is that
term by term? So basically, it's a parametric statement. So basically, as long as you are always below or you are always above the cutoff scale. So as a parametric sum, so the leading term is always 1 over sigma term.
I see.
It's basically like, again, the analogy is effective field theory. So there you have terms like this, but obviously there are like terms which are suppressed by higher power of the cutoff scale. They are all also there. But in the domain of validity, they are always suppressed compared to the leading term.
Okay.
And also, let me make a couple of more comments. It's basically the same theorem or same techniques can actually be used to derive the Nachman theorem. So this is basically you can derive exactly the same sum rule even for the case where eta is the smallest quantity. So here you take eta to 0 first, then sigma to 0. Then you can derive exactly the same sum rule. In that case, this CL coefficients, they are basically sum order 1 quantity times eta to the power twist of the exchange operator. So from that fact, basically you can derive the Nachman theorem. And finally, let me make one more comment. So even though I derived everything for scalar operator, for a single scalar operator, you can easily generalize this for even when you have multiple scalar operators or even when you have spinning operators. The same statement that the same kind set of constraints that I derived, they should be valid even for spinning operators. In fact, it's very easy to show if we start with things like Rindler positivity to begin with, then generalization to spinning operator is almost trivial. But if you want to start from the OP expansion and unitarity alone, then this requires some work, but from Rindler positivity, this is completely obvious. Okay, so this is where let me just tell you what I'm going to do in the next lecture. So in the next lecture, okay, so the goal of next lecture is basically now we have all these consistency conditions. So we have this safety, consistency, condition. So this was lecture 1. So this is lecture 2. So in lecture 3, I am going to use this consistency condition to derive bounds. So that's the goal for the next lecture. Let me stop here. Thank you very much.
Sandipan, can I ask a couple of questions? So your technology, are they going to give you two-sided bounds or only one-sided bounds?
Two-sided.
And is that going to be quite general or only for few cases?
General in the sense that basically, depending on what you mean by general, so it's basically I'm going to write down.
I mean, general means that would you be able to show it for arbitrary coefficients, or is this just a case by case, and then you sort of conjecture that it is going to hold generally?
No, it's basically I'm going to write down an effective field theory of a scalar with basically anything of the form phi square box k phi square. So any such interaction. Basically, okay. I'm going. Other than that, there is no additional condition that I'm going to impose. No.
Okay. And the other question was that I mean, Slava in these Bootstrap series made sort of a claim that the assumption about the T-channel convergence apparently is not completely rigorously justified. So what is your take on that?
So let's see. I'm not actually.
Yeah.
Go ahead.
I mean, he gives it a name. He calls it the Llss Conjecture, and he was saying that apparently this was what was used in the proof of NEC, and he feels that it is not completely justified. So
I'm actually not aware of that claim. So basically, when you say T-channel expansion, do you mean on the Lorentzian case or in the Euclidean? In the Euclidean case, it should be
in the Lorentzian case, I believe.
In the Lorentzian case, it's a known thing that it's an asymptotic series, but it's not a convergent series.
Mm-hmm.
So term by term, it's fine, but they are just like any asymptotic series, like it can break down if there is some accumulation point, things like that can happen. But yeah, you have to always keep in mind that it's an asymptotic series.
Okay. Okay.
And
yeah,
the thing that I actually don't know, like how rigorously one can show that it's an asymptotic series. It's something that
I see.
We always say, but probably Slava knows more about that. Like probably it's kind of difficult to show that it's like honest to God asymptotic series.
I see. So that is the point. Okay. Thanks.
Yeah. So, but that I don't think that's even for the standard light cone bootstrap. I think that problem is already there.
Yeah. No, in the light cone bootstrap, I think there are issues that Slava feels have not been rigorously solved. But I just wanted to hear it.
Yeah, but even in light, it's basically the thing is that when you take the light cone limit, or like if you take the Lorentzian any limit you like, as soon as you go beyond the Euclidean regime, so there is an issue about like summing the series and taking the limit, or taking the limit first then summing the series.
Right. No, I understand the point. Yes. Okay.
Yeah, that's the issue. Yeah, that's the main issue.
Okay. Any other questions? There are a few. So Sachin, since I don't know whether you heard, next 18th lecture is going to start at 10 o'clock. 10 a.m.
On Monday?
18th.
On 18th.
Yeah, okay. That's the third and final lecture. That is going to be at 10 o'clock.
Okay.
Yeah.
Okay. Can I ask one very quick thing? So scattering matrix in the in your EFT. So here you are able to get some constant on CL, etc., and then you are going to use that to constant your scattering amplitude, right?
Yeah, basically like so in the effective action, there will be terms like this. There will be terms interaction terms like this.
Yeah.
So basically, I'm going to relate CL to this lambda K.
Yes. So the question I was asking is that, is it possible to relate the actual 4-point scattering amplitude to directly some correlator? I don't want to match the coefficients.
Yes. So actually there is already a paper by Karen Huart, I think Mazak, Rastelli, and Simon Stephen. So basically, what they are doing is basically exactly what you're asking. Is basically they are starting with some safety correlator, which is exactly like some ADS scattering.
I see.
And then obviously, like you can do that, and then you have to use other theorems to actually constrain those safety amplitudes or safety correlators. So yeah, so this technology will not be useful there.
This technology will not be useful. Actually, so I have a question to, if Anindra, can I ask you something very quickly in a minute?
Sure, yeah.
You had this beautiful paper where you had used information theoretic quantity to constrain the scattering matrix, right?
Yeah, some things, yes.
Yes, some things. Now, would this be a nice route to actually use information theoretic quantity to directly go and start constraining CFT correlators or CFT things other than the other machineries? Like I know the relation between scattering matrix and the CFT correlator, and then I know how you actually implemented, and people have been doing this kind of thing, information theoretic quantity. And that will actually give you a nice way to start implementing information theoretic quantity inputs into the CFT correlator.
Yeah, I think it should be possible. You have to, first of all, identify a suitable density matrix, and then it will become various constraints on that density matrix. I think definitely it is possible. Yeah, I've thought about it from time to time, how to use these kind of things more in a cleverer manner. So from the S matrix point of view, there are these things called entanglement entanglement power, and that entanglement power is some quantity that was introduced in the from the perspective of nuclear physics, and that seems to have some very nice interesting behavior for physical theories.
Right.
So those kind of things can definitely be done for CFT as well. It's just that nobody has. In fact, it's a good thing to ask Sandipan as well. So how would you define a suitable density matrix in this case? I mean, is it simply that you take two of the operators acting on the vacuum and then call it state one, and then using that you define a density matrix the usual way that we would do it?
It's actually kind of tricky because like the way operators are inserted, that might not be a good interpretation. Let's see. Yeah, actually that's kind of a conceptual issue. Like the correlator for which we can derive this kind of analyticity and positivity conditions, they don't have those kind of interpretation. And the correlators that can have those kind of interpretation, for them, it's kind of difficult to derive these conditions.
So if I can just say one thing, Sandipan, when you said this Karan paper, they really match the correlator with the S matrix. S matrix is done in the momentum space, and that's where Anindra also did all his information theory. So if I can define something in momentum space, they will be much more easier to do the implementation, I think.
I actually don't remember the exact procedure, but I don't think they. So there are a series of papers where actually like there are proposals how to actually relate a position space CFT correlator with a momentum space amplitude. So
or you can Millen space, right? I mean, that's an easier what Joao and company taught us.
Easier, but I'm trying to remember all the conditions that I'm aware of. None of them are on the Millen space. Like
so Millen things have not been worked out. I agree. I mean, these kind of things have not been suitably worked out in Millen space, but it is possible in principle. I mean, it's not.
I'm not just that. My belief. I actually tried this once, but like not. It's not that I did. Like I spent a lot of time. I think there are very nice statements about the Mellin amplitude as well, which people don't know about. But like, for example, like if I just ask you, so if I give you a CFT correlator in position space, I know everything about causality and causal structure. But for the Mellin amplitude, it's kind of non-trivial.
Yes, absolutely. No, yes, you're talking about the so what is the interpretation of the Lorentzian versus Euclidean?
Exactly. Even like even the fact that even the fact that like I know where exactly the branch cuts are in the position space.
Yes.
What's the corresponding statement about the Mellin amplitude? I don't actually know that statement.
Right. Yeah, I agree that people have not worked it out fully, but it should be possible because after all,
And I guess that's a important route to take. I think like those kind of things actually will be more useful to actually relate amplitudes with safety correlates exactly, like not just like some kind of like philosophical equality.
Yeah, I agree. Okay, I'm going to stop. So actually, Parthiv can stop recording and then.